Welcome to this second epilogue in our Radio Design 101 series. As you may know, Radio Design 101 is a collection of about 10 videos where we learn how to design, build, test radio circuits. But then we started epilogues. These are things that came after we finished the receiver. And in epilogue 1, we looked at the performance of the receiver, which we'll review today, but we also broke it. And so what's important about today's material is that A, we're going to fix that, but more importantly, the things we do to fix it are general. They could be used to troubleshoot anything for the most part, including even automobiles. We'll show an example of that. There are some other videos down here at the bottom as well that support these university level classes. These are about test equipment. And you may know about the Nano VNA or the Tiny SA, Tiny Spectrum Analyzer. They're invaluable for doing this kind of design work even at home. So here's the radio that we designed and built in the Radio Design 101 prime sequence and tested in epilogue 1. It's a super heterodyne receiver designed to receive the FM broadcast band. And there are filters and low noise amplifiers, and then a mixer to translate the frequency down, where we do the final channel select filtering, and then we amplify it and demodulate it. The various physical components are shown over here on the bottom right, and consist of the low noise amplifier with some of that filtering in it, and a mixer here, and an IF amplifier and the demod. The audio section, we just piped the audio out of the demod and went to a powered speaker. This is the Tiny SA, and we're using it to generate a local oscillator signal so that we have a synthesized radio. And when we're all done, we tested it, and it worked, and that was incredible. But like many engineering endeavors, it didn't work perfect the first time. It did, however, work well on, let's see, 1, 2, 3, 4, say 5 stations. We picked up very well, very clear. We also compared how our receiver worked to a commercial radio called a VR120 by Yaesu. That's this little guy right here. And you can see that we didn't perform quite as well. The main reason has to do with the signal strength of the various channels. There's a very strong station in our area that comes in at about -22, -23 dBm. And then there are very weak ones, some of which we got and some of which we didn't. So we'll start by reviewing the problems that we found in epilogue 1. And those problems are a combination of things that we didn't do perfect in our design, but also of the environment in which radios live. Very strong stations can end up blocking weaker signals like these ones down here. This is from 85 megahertz to 110 megahertz. So this is the entire FM broadcast band, and -20 dBm is this line, -30, 40, 50, 60, 70, 80. So we've got signals down here that are -80 dBm in the presence of very nearby stations that are around -20. So we'll look at why that caused problems, as we found in epilogue 1. In epilogue 1, we also then proceeded to try to fix it, and we ended up breaking the receiver. It just stopped receiving signals at all. And today's episode, we're going to use that as a way of illustrating troubleshooting. But remember, this is not about fixing one little problem in one particular radio. Today's episode is about how to do troubleshooting in general. And then finally, we'll present a few future topics. And one of those in particular is, I think, extremely valuable. And that is the creation of new circuits, and in fact, new circuit techniques that may help in all radio designs. So we're going to talk about, briefly, something called Q-enhanced low noise amplifier design. We'll do that at the end of this video and go into more depth in a future video as well. So here's what we found to be the main problems in our radio. The front-end bandwidth, that's the bandwidth of this filtering here, fore and aft of the low noise amplifier. The LNA was peaked in the center of the FM band, where the signals were very strong, or at least this one was, but the filters rolled off at the top and bottom end of the band. So over here on the left, that's these blank areas here, And up here on the right, that's these blank areas here, and our radio is not picking those up. Part of the reason for that is that we found the mixer to be overdriven in our area because that station in the middle, it hit this low noise amplifier with minus 20 dBm, and then the amplifier amplified it up to 0 dBm. And so that came into this mixer, which had what we found to be a compression point of about minus 20 dBm. So we were hitting this mixer with way too strong a signal. And that resulted in what's called gain compression, and we lost about 20 dB of gain here. So even though we designed this system to receive signals down well below minus 80 dBm, we couldn't get things below about minus 55 or minus 60 dBm because we lost 20 dB of gain here. Other things we found, the IF filter, which is supposed to select the one channel you want and pass that on to be amplified and demodulated, had limited off-channel rejection of about 50 dB. So that meant that these stations right here, and certainly that one, would be blocked by this one. But in our defense, the commercial receiver, this VR120, did not pick up those stations either, unless we turned on the attenuator, and even then there was a station that it couldn't receive. But we should have been able to receive everything above this line here, and the reason is because we had gain compression in the mixer. Now we'd like to stop that, but it's easier to maybe just up the gain in the IF amp. So in principle it was a simple thing that we could change to get those stations. This is the IF amplifier, which is covered in one of the episodes in the main series of Radio Design 101. So I'm not going to go through the details on that here. However, we've pulled out a couple of the main equations. The voltage gain of this amplifier is the transconductance times the resistance. What resistance? Well, this R4. So if we pull that resistor out, then the R in this equation should go up. Might look like it goes to infinity, but in fact there's some parasitic parallel resistance in this inductor. There's an input impedance looking into this Q3 amplifier and so forth. But it should have gone up quite a bit. We should have gotten at least 10, 15 more dB of gain. We also found that the IF amplifier was not centered at 10.7 megahertz as it should be here. Instead, it was centered around 6 or so. So in order to address that, we just pop out C4, and that should raise the frequency. C4 resonates with L1, but remember, other things matter too. There's capacitance in Q3 and capacitance in the output of Q2 and some parasitic capacitance in this inductor. However, it should have, according to this equation here, caused the center frequency to go up. What happened instead is that the entire receiver lost sensitivity everywhere. And we found some pretty strong clues that that was due to this amplifier now oscillating, which is a very common problem in high-gain radio frequency circuits. So we've got a quick video here to show why we think that's the case, why we think it's oscillating. Now, in this video, I'm touching the circuit. And don't do this on anything that you don't know what you're doing and anything that's high voltage or high power. This is a low power circuit operating on 5 volts, and we designed and built it so we know what we're doing. Let's take a listen. One possibility is that it's got a bad solder joint and sensitive, but if I poke around with this insulated tool, I don't get anything. But if I put my finger on it, it reliably works. Tremendous. So that's a pretty sure indication that it's oscillating. When I put my finger on it, it loads the circuit and it stops the oscillation. Now, fixing oscillations can be tricky. The first thing that we need to check is that we didn't mess up something on the circuit when we desoldered these components. Ask what changes were made since the last time it worked, and what changes were made is we took these components out. So we could have messed up the soldering here. To check on that, we visually verified and checked it with an ohm meter that the connections were okay. To go a little bit further, we verified the DC bias voltage at VCC up here at the top, and also at the base and emitter of these two transistors. And that pretty much tells us that we didn't mess anything up here. However, we could have shorted L1 and we wouldn't detect that, but we visually checked that. So what we did next is we probed the signal at the IF output, which is right here. So let's play a couple of video clips here to see how we did that. And again, warning, this is only for low voltage, low power circuits that you're fully familiar with and you know what you're doing. Also, to protect the test equipment, Tiny SA here, you in general need a DC block because you'll have some DC voltages, and you probably want an attenuating probe. So to test for the oscillation, we're going to use a little Tiny SA spectrum analyzer that we've used throughout this series. And I have it hooked up to a probe that I built using a SMA male to SMA female connector and a half-watt resistor that I had lying around. It's 330 ohms. So looking into the coax terminated in the Tiny SA, it's 50 ohms. So it's a little less than 10-to-1 reducing probe, but it won't load the circuit too much. That's the point. So I'm going to attempt to probe it while holding the Tiny SA so that we can see it. It's sweeping from 0 to 30 megahertz. And so a third of the way along is 10 megahertz. It's about where we should see the 10.7 megahertz. If it's oscillating at around 6 megahertz, which I think, it should appear around here. Anyway, let's take a quick look, see if we can catch it. So touching the ground and the center lead. Yep, there's the oscillation. It says 5.97 megahertz for sure. If I touch it, see if I can make it go away. Yeah, it went away, and notice the other one that... Notice the 10.7 popped up and you can hear the signal. If I stop touching it, it stays working, but then I released the load and it comes back. So the oscillation is a little tenuous. It's definitely back, and I can make it go away again by touching it, and I can hear the station. So here's what we know now. Touching here caused the oscillation to go away. And in some cases, the oscillation stayed gone after we removed the finger, but removing the probe could start it up again. So I'm going to call that a kind of a sticky oscillation. So with those clues, we now need to develop some theories so that we can make some changes and hopefully fix it. So here's what I went through. The clues include the frequency. It's 6 megahertz. Now, that's the same as the original frequency of the amplifier, but remember we removed the capacitor and it should have gone up in frequency. Also, the oscillation is, in some sense, sticky. Now, as we learned in Radio Design 101, oscillation can be created by doing feedback. So we might look for some feedback in this circuitry, and we'll do that in a second. There's also a common thing that can occur in radio frequency designs when you use one of these emitter-follower amplifiers or common collector designs if the output is capacitively loaded. But in this circuit, we have R5 as a 1 k ohm resistor, and we are taking the output from here, and so I don't think that's the case. So we ruled that out. So the remaining theories have to do with feedback. The final output of the amplifier is here, but there's a primary output right here. And I suppose we could get some feedback through this path, but you know what? C7 is supposed to be an AC ground. So there really shouldn't be a path for any currents that Q2 pulls through L1 to generate voltage here that would then get around to here and get back into the amplifier. In addition to that, this is a 10.7 megahertz filter. The IF amp is to the right of the vertical line I'm drawing here. This circuitry on the left is an abstract view of what's at the mixer output, and this is the filter at the mixer output. But in any case, there shouldn't be a path around this loop. So we're going to look somewhere else. Maybe there's some voltage, RF voltage being induced on this line because C7 is not a perfect bypass cap, and we know that from the parasitic discussion in Radio Design 101. If that's the case, then any RF voltage on this line, which is supposed to be quiet, but if C7 is not a perfect bypass, it could come back into here and form a loop, or down into here and form a loop. But even though there's some inductive parasitics with C7, the layout was done in such a way that it's a very short path and there shouldn't be much inductance and we shouldn't have had a problem. However, that capacitor is up here and there is a line, which is this red line, which goes to the power supply. So that red wire, we know from Radio Design 101, has inductance associated with it. Even though we dutifully twisted pair the wire with the black ground wire, it still has some inductance because it's fairly long. It's several inches long. And so we just made a guess that maybe there's enough length there that we have maybe 100 nanohenry of inductance on that wire. This L3 here is not part of any of this circuitry, not part of the intentional part of the circuit. L3 represents the inductance of the wiring here. And where does that wiring go? Well, it goes back into this board, which has a bypass cap. That's C8 over here. But notice what we've got here. We've got C7 to ground and now L3 to ground through C8, which is actually bigger than C7. So it could be that we can model this as C7 to ground and L3 to ground. And they're in parallel. And what is that? It's a parallel resonant circuit. And if you run the numbers, 10 nanofarad and 100 nanohenries works out to be pretty close to 6 megahertz. So if that's the case, then what happens is this line is not AC grounded. In fact, it's a fairly high impedance looking from this point back into the power supply. So as Q2 pulls current through L1, it generates a fairly substantial RF waveform right here, and that can loop back around and get into these transistors. I'm not going to go through all the phasing and so forth, but it's quite possible that that's what's going on. So that's what this bullet here is talking about. The last bullet is looking at what's making it sticky, but that's not really important. Let's move on. What's really important is that we've now got a decent theory that C7 is resonating with the inductance in the power supply leads. And the question is, how do we fix that? And the answer is, the proposed solution includes adding a series resistor in the supply lead. So right here where this red wire comes in, instead of going directly to that capacitor bypass, we go through a 20 ohm resistor here. So we soldered this new resistor in and we put it right here. I haven't drawn it in the schematic. It's small enough, it's not going to create much DC voltage drop, so it shouldn't affect the circuitry. This should bypass the voltage then, but the parallel resonant circuit should be dequeued. It should reduce the Q of this circuitry so that when you stand on the VCC line here and look out this way, you see primarily C7 to ground, and this L3 now has resistance, and so you're not going to get resonance between this capacitor and inductor very much. And so C7 will serve its purpose. And in fact, you may recognize this as a common thing that was done in some older designs. People would routinely put some small resistances in to form sort of a low-pass filter. Here's what it looks like, but it's also dequeuing these resonances. Of course, conventional wisdom like that can sometimes be lost as we move forward, especially as we're decreasing the size of circuits and we don't have exactly the same reasons to do what we did before. But in modern books and papers and PC board layout guidelines that you may find on the web, these bypass caps, they are still a problem, especially at radio frequencies and even in computer designs. And if you want to look into that, Google a term called power integrity. And you can find a lot of literature on that. It's a very important problem, especially in high-speed digital circuits these days, but also in RF. So, definitely working much better now. So, not only is the problem that we created fixed, but the original goal of increasing the gain has succeeded. The new test results show that we can get about twice as many stations as we could before. We still have problems at the low end of the band and the high end of the band. And we still have some problems for weak stations like minus 80 dBm nearby to really strong stations like minus 22 dBm. But so do these other radios. So we're almost there. remember, the point of this video wasn't to fix our radio necessarily. The point of this video is to talk about troubleshooting. So let's review and generalize what we've done. So I'll talk through these steps briefly, but you could also pause the video here and think back through what we did and try to commit some of these things to memory if you don't already know them. I've found over several decades of engineering work that these apply to just about any system and problem you might run into. So the first thing you want to do when trying to debug or troubleshoot a problem in your circuit or system is you got to understand that circuit or system. You can't fix it if you don't know how it's supposed to work. You also need to review any safety issues. Make sure you're not going to put yourself in danger or somebody else in danger. The next thing I always do is ask what changed since the last time it worked. And in our system, that was we desoldered some components. So we looked carefully in those areas to make sure we didn't mess something up there. Turns out our problem was, in some sense, a design problem. So sometimes you're troubleshooting a system that is well designed and has been debugged in advance and it just stopped working. In our case, we were taking a new engineering design and basically making it work better by finding some bugs in the design itself. Along the way, we did break it and then fix it. All right, so how do we fix it? We assess the known symptoms and we tried to localize the problem. We knew which area of the whole radio we were messing with. So the asking what changed since the last time it worked gave us the localization into the area of the circuitry that we should be looking at. If you don't know that in advance, then that's the first thing you should do. Try to localize the problem based on the clues, but maybe also some signal tracing. Do some quick checks visually under the microscope, but also check the DC biases. That'll tell you a lot. And in any troubleshooting thing, there's a tendency to look for common causes, common problems. But don't overemphasize those. I'll show you an example of that in a minute. Quite likely you'll need to collect some additional clues by injecting known signals and doing some signal tracing. We did that in this example where we found the oscillation. And then develop some theories and then test those theories. But consider the keep it simple principle and time and monetary cost as you're doing this. Order your procedure in such a way that you don't do the expensive things first. And finally, recognize that if there is a fault, then it may change the circuit. So the circuit may be different than we thought it was. And we saw an example of that in our case where when it was oscillating, we thought there was a bypass on VCC, but in fact that bypass was corrupted by some inductance in the power supply lead, so it wasn't a bypass there. And ultimately this is a puzzle and you may need to sleep on it and come back with a fresh start. So these are general troubleshooting techniques. I actually applied these to my Corvette one time when it stopped working. And I'm going to skip these slides right now and come back to them after we finish up this real video. But if you stick around to the very end, then I'll show you how I saved days of work and hundreds of dollars by following these steps. All right, so that brings us to pretty close to the end, except that I do want to show you what we're going to talk about in the future. We'll do some more epilogues in this Radio Design 101 series. And some of the topics that we're going to look at is why does this radio, this old radio, work even better than this one down here? So we're going to study some commercial radio designs and their associated schematics. And that'll bring up performance considerations. We met compression points in this video, but also in Epilogue 1. Other topics we'll look at: spurious products out of mixers. A very strong signal here mixing with a very strong signal here can actually overwhelm some of these other signals. And that deals with something called intermodulation. At the other end of signal level issues, instead of having signals that are very, very strong, you could have very, very weak signals. And so that brings up what is the weakest signal you can receive. And that brings in things like noise figure, minimum discernible signal, etc. Unfortunately, in today's world, that's not always that important because there may be elevated noise floors in the environment. This spectrum analyzer plot can only see to within about 30 dB of the lowest theoretical possible signal that I could get. So in theory, I could receive signals that are 30 dB below this noise floor that you see here. But in practice, when I tried to do that by putting an amplifier ahead of this spectrum analyzer, what I found was in my house, the noise floor was 10 to 20 dB above the theoretical minimum. And this is getting to be a more known problem these days. Not too much you can do about it because this radio frequency interference that's raising the noise floor everywhere is coming from modern switch mode power supplies, which are in everything, and especially lighting, LED bulbs, for example. So we're going to concentrate primarily on the strong signal performance issues and how to defend the receiver against these really strong signals and receive very weak ones, like maybe that one right there. And personally, I don't think all of that stuff would be a lot of fun if we weren't designing some circuits to illustrate and to make these things work. That was the beauty of the senior level design course that the Radio Design 101 series is centered on. We actually designed and built circuits in the lab. Here, I've got a new circuit that I'm putting together and trying out to address this problem of receiving a weak signal like this one in the presence of a strong signal like this one. So this one is, in fact, 55 dB higher than the signal I want to receive. And we've seen how that causes problems. Now the question is, how can we fix it? Number one, we need to make these filters tunable. And so there's a couple of potentiometers here. One of these potentiometers adjusts the frequency. There's a varactor diode right here that is tuned with this guy. Another one of these does some Q enhancement by feeding some of the output signal from here back to the input of this amplifier filter system. And when we do that, the response peaks and becomes very narrow. This is from 88 megahertz to 98 megahertz. These spectrums are as well. So we're just seeing the bottom half of the FM band here. You can see that it peaks at around 28 dB gain. The bandwidth is quite narrow, say 200, 300 kilohertz wide, about the width of a single station. So when we put this circuitry between the antenna and the rest of our receiver, if we swap out our current low noise amplifier and filtering with this, and we tune it so that it's centered on this very weak station here, we can bump this one up by 30 dB or so while simultaneously reducing this other one a little bit maybe. But the result is that we now have a signal to interference ratio of 20 dB instead of 55. And that allows us to receive this very weak station here. So we'll end with a little listen to that, and then we'll go into the Corvette for anybody who wants to stick around.
Monday evening, look for mostly
Here we are, Radio Kansas.
15 to
Very
20
difficult
degrees.
to get in this area.
Our current temperatures here at Radio
Coming in
Kansas.
perfectly
In Hayes, it's
due
27
to our
degrees.
amazing new
Great
filter.
Bend, 36.
Yay.
Hutchinson is 28. Wichita, 30 degrees. This is the Radio Kansas Network. 90.
And we're back. For anybody who stuck around till this point and wants to learn about a Corvette and a problem that occurred and how these troubleshooting techniques were used to fix that problem, here we go. So here was the problem. I was out driving around and I smelled some antifreeze, and in fact it was leaking under the dashboard here. So there's a heater core in this Corvette. You can't see it, but it's back here somewhere, and it was leaking into the cabin. So when I looked up how to replace that heater, well, first of all, I did not have a heater core to replace it with, so I decided to bypass it. I also found out that you basically have to take the car apart to change the heater core, so didn't actually change it, just bypassed it. So in the process of bypassing it, these hoses had to be disconnected, and that let air in, and so the antifreeze that goes through these hoses had to be purged of air. So there is a little vent over here that you have to open and then run the car and let it circulate and get the air out. But that also gets some water out, and what happens is the water then, or antifreeze, pours down over the engine here. And oh, down in here there's something called an OptiSpark, which is a fancy name for an electronic ignition system timing device as well as a distributor. So it's a scary thing to do this because those OptiSpark things are known to be endangered by getting wet. So I get the job all done and get it all burped and get all the air out, and then get in the car and turn the key, and guess what? The starter goes, but the car won't start, and my heart just sunk because I know what a pain it is to get into the OptiSpark. It's behind the water pump here, and so you have to take the whole front end of the car apart, it seems. So it's a very huge job. But after that moment of trauma, I had an idea. Let's go into some troubleshooting. Let's not make the assumption that the common cause is the cause in this case. Don't overemphasize common causes. Could be something else. So the question is, how do we find out what it is? How do we localize it? Well, the problem is the car is cranking, but it's not starting. So I had to understand the car, and I also have to understand safety issues of the car, right? So you can damage yourself. So I understood these things because I had the manual on the car. So that was good. So I knew where to look. So I found the ignition coil and was able to, I think I put a timing light in or something to check to find out if there's a spark being created. Got to be careful about that. So I think I was using a timing light or something safe. And there was no spark. Yikes. Well, that could be the OptiSpark system. That's that common problem that everybody says when this doesn't work. Oh, you've got to replace your OptiSpark because they're terrible. But remember, I had the manuals for the car. And the manuals describe exactly what that OptiSpark does. And one of the things that it does is it sends a signal back to the engine control computer that then sends a signal to something called the ignition control module, which is this little electronic block right here, that then creates the spark with this big coil here. And it gets an input from the OptiSpark on this connector. And that input is supposed to look like this. It's a little 5-volt pulse. And if the OptiSpark wasn't working, then that pulse wouldn't be there, or it would be incorrect. So I did signal tracing. I took the signal that was supposed to be coming in to this connector. I disconnected the connector. I put a resistor in here just to be safe and not short stuff out. And then I connected that up to the oscilloscope and cranked the car, and I saw this pulse. And I'm like, oh my goodness, this might be okay. It may simply be that this unit is bad. This is actually the old one over here. So I pulled it off of the head here, and then I bought a new one and got it together and put it back on. And to make a long story short, the car worked. So that probably saved 12 hours or more and many hundreds of dollars that would have been needlessly done if I had just gone with the conventional wisdom, because I followed these procedures. So once again, thanks for watching, especially if you got this far. We'll see you in the next video.